This is Kettering University.
Good afternoon, ladies and gentlemen. It's my great pleasure to be here and to give this talk to you. I will try to give you a general information about the research, what's going on the electrochromic windows and devices. First of all, let me define what is electrochromism. Electrochromism is the reversible modulation of visible and near-infrared radiation under the application of external voltage. It could be DC voltage or AC voltage, but if it's DC voltage between 1.2 up to 3 volt. As you've seen in here, this is on the bleach side of the device. And when you apply the electric current on it, the device colored generally dark blue or brownish blue. I brought a sample with me that I developed, I assembled in my lab at Lawrence Berkeley National Lab. It has been assembled 6 years ago, still works. I believe it will be working for up to 20 years. We will see. And electrochromic windows. Why we want to use the electrochromic windows? I'm going to start selling the windows, of course, start with the advantages of the window. First, offers substantial benefits by increasing the thermal and visual comfort, reduce the energy consumption in a building, reduce the peak electric loads by up to 20 or 30%, and reduce the cooling, heating, and demand for the electricity. And electrochromic windows will be the key contributors towards the advanced building technology, which will conserve the world energy resources. Switching time of device depends on 3 factors. One of them is size of the device. Second, operating voltage and operating temperature too. Generally, those devices can be operated between 30 to 70 centigrade degree. I'm sorry, as you see on my resume, I get my education from Europe, so I don't get used to Fahrenheit, and I use the international unit system, so you will hear a lot of meters, centimeters, and so on. I'm not going to convert to the US custom system. Sorry for that. And the applications. Most successful application is in the automotive rear view, side view mirrors. The market is really big. It's about 15 to 17 million per year. Most of the US cars and most of the European and Japanese cars use those mirrors. You may not know, but BMW, Mercedes-Benz, Infiniti, Nissan Infiniti, and Lincoln cars uses this technology. It is so, I was so happy today. I'm coming from Detroit. I took a Lincoln car to the airport as a taxi, and I was talking with the person, the driver, and he told me that this car uses some kind of mirror that when he drives, there is not much glare during the nighttime. I say, yes, I know. You know, that's my research field. So I developed a conversation with him, and he learned about why he operates like that. His car was using electrochromic rear view mirror and side view mirror. So I saw today myself that it has been used in the cars. And new markets, this is an upcoming market, AC windows for transportation industry. These are the small electrochromic windows, which is the size, the area is about 0.7 meters square, airplanes and sunroofs. Actually, you heard about the Dreamliner, right? The Boeing 787. The first class and business class uses those electrochromic windows in their airplane. The other application for the airplane, Airbus 380, also uses same electrochromic windows, of course, in the first class and business class. The ones that used by the Boeing 787 developed by Gentex and PPG Glass. PPG stands for Pittsburgh Plate Glass Company. And the other one, the Airbus, has been developed by Saint-Gobain Glass Company from France. There is the largest glass producer in the world is Saint-Gobain. You may not heard about that, but Saint-Gobain is the #1 company. And also, it can be used for large area electrochromic glazing for the building size. The size is 2.6 meters square. On the right-hand side, you can see the electrochromic window. Upper part show the colored state when you apply the voltage. The applied voltage is 1.7 volt in this case, and the bottom part is in the bleach state when you don't apply the voltage. And this is actually taken from the Uppsala University. They developed this device, and when I visit them, they show me, and I took the picture. So it's from the Uppsala University in Sweden. Common components of an electrochromic device. Generally, those devices fabricated in a sandwich structure. The first structure is glass substrate coated with a transparent conductor. Both sides of this device is glass, but on the top there is a transparent conducting material. See, both of them glasses, coated with a transparent conductor. And then electrolyte layer. Electrolyte layer contains mobile ions in it. It could be protons or lithium ions. And redox material. Redox material is the part of the device where the coloration occurs. I'm going to classify them, what type of redox materials are they. And devices works by the exchange of electrons and ions. Ions are transported by the means of electrolyte, electrons by the transparent conductors. Redox material, which is electrochromic materials, can be in thin film form. My expertise is making the thin film coatings, and or in a solution in the electrolyte. The car mirrors mostly use the electrolyte system. They don't use the thin film system, but Windows uses the thin film system. Now, transparent conductive materials. We have two types of materials commercially available. You can buy it from Pilkington Glass in England, or you can buy it from PPG in United States. The requirement for transparent conducting glass is high transparency and high conductivity. Types. I'm going to start with the inorganic ones. There are also organic ones. You will see in the next slide. The most used ones is thin doped indium oxide films which is called as ITO. ITO films generally deposited by the physical vapor deposition technique. The most used one is sputtering technique, and most widely used on all transparent conductors. With shortage of indium metal, need to find an alternative material replacing with ITO. And then they find the fluorine-doped tin oxide films, which we called as FTO, another inorganic material. FTO is deposited by the float line by atmospheric pressure, such as chemical vapor deposition, CVD, or it has high conductivities, which is less than 10 ohm per square. And the coating, the disadvantage of the FTO is the haze. It has a little bit hazy. It's not as transparent as ITO. Then this makes it limited use, especially if you are using it for the Windows application. There are also alternative transparent conductors. They are organic transparent conductors. Conducting polymers, we call as PDOT, and transmittance above 90%, which is good, but electric resistivity is higher compared to the inorganic material. It's less than 400 ohm per square. Disadvantages like as all organic materials, they don't have long-term stability. Polymers can be destroyed, their properties very soon. So PDOT degrades over time if exposed to the light or heat. That's the big disadvantage of it. There is another material which is called as C12A7. This is also electrochromic material, both transparent conducting and electrochromic materials. Turns green by hydrogen incorporation. Disadvantages, the current properties are from possible applications in electrochromic windows, but they are not suitable for the other applications. Now, one of the most important components of an electrochromic device where the mobile ions can move easily, insert and extract from this material are electrolytes. Electrolytes can be grouped into two categories, liquid or gel electrolytes. As an example of liquid or gel electrolytes, is lithium salt. Conductivity and concentration is very important. You need to use solvent, and you also need to use thickening agent or solidification agents. You need to add UV stabilizer too if you want to use the liquid or gel electrodes. There are solid electrolytes, mostly made by the physical evaporation or wet chemical deposition techniques. These are the examples. The most used proton conductor is titanium pentoxide, zirconium oxide, and for the lithium nitrate, lithium aluminum fluoride, lithium niobate, lithium titanate are the most used examples for these electrolytes. Now, inorganic redox materials, which this device uses an inorganic redox material. I will tell one of them, the working electrode, but I'm not going to mention about the complementary electrode because this is a confidential study, the other part. So inorganic redox material are the materials where the coloration occurs in the layer. The most used one is tungsten oxide. The electrochromic property of tungsten oxide first observed by a researcher, Dr. Satyen Deb, from National Renewable Energy Lab in Golden, Colorado in 1963. So he first observed this, and then the research took off on that area. If you doped tungsten oxide with another material, or you can use the composite tungsten oxide material, you get the better property for the coloration and more natural color. Like here, you can dope tungsten oxide with palladium, or you can use the composite tungsten oxide, vanadium pentoxide. Also, molybdenum oxide has the same property, and this is another composite material example, molybdenum oxide, tungsten oxide, molybdenum oxide, titanium oxide, and so on. Cathodic materials colored when they are reduced. Anodic materials color when they are oxidized. So it's the typical example of those materials are iridium oxide, nickel oxide, silicon oxide, nickel oxide, nickel hydroxide, and so on. There are some materials that they have colored or colorless in the reduced or oxidized states. Those are vanadium pentoxide, iron vanadium oxide, sodium vanadium pentoxide, niobium vanadium pentoxide, and so on. Those are the materials. Generally, you always, in a device structure, you always use two of them as a complementary. If one of them is cathodic material, the complementary layer should be anodic material. So this device has two electrochromic layers. One is cathodic material, which is tungsten oxide. The other one is anodic material. I am not going to tell you, but it's a composite material. And now let's look at the organic electrochromic materials. Viologens are the most known organic materials. Pyrrole and another polymer electrochromic material is polyaniline, we call that PANI, and also P-dot. Those are the organic electrochromic materials. Now, let's look at the electrochromic device composition. They could be categorized into four different types. One of them is solution-based electrochromics. Second one is electrochromic devices incorporating solid and electrochromic films, ion storage layer devices, and devices containing both anodic and cathodic layers, which is the example you see here. This is the example of device containing both anodic and cathodic layers. Now, I will start showing how the colorations occur in the solution phase electrochromics. Basically, you have two glass coated with transparent conductor. These are the glass, and those are the transparent conducting layer. And you put between them, you sandwich electrolyte. Liquid electrolyte. This is the type of device that the most Gentex mirror use. Contains two redox species, one of them in the color oxidized state, the other one is in the reduced state. Reactions occur at the cathode and anode in this type of device. Now, solution phase electrochromics. You can see over here, this is taken from the Lincoln car's rear view mirror. It's in the high reflectivity state, and here when they colored, you see the low reflectivity, no glare. Here you will see a lot of glare, but on the lower part you don't see any glare. So in this type of device, the applied field potential lies completely to the left colorless solution. Once the potential is removed, self-bleach form a lower energy colorless form. This is the redox reaction 1 and oxidation reaction 2. Applications: rear view electrochromic mirrors for automobiles. Gentex mirror that has been located in this state is Zeeland, Michigan, uses this technique. So self-bleaching and power requirements to maintain the colored state make them unsuitable for the architectural glazing. They're okay for the mirror application, but not for the architectural applications. Now, devices incorporating solid electrochromic films, they consist from ion storage layer, anodic and cathodic electrochromic materials. I call them as a complementary materials, and working material and counter electrochromic layer. Redox promotes in the electrolyte. This is the sample of those type of device. Now, ion storage layer electrochromic device consists from glass and transparent conducting layer coated glass. There is an electrolyte between them in the center, and we have a working electrode, and we have a working electrode and complementary electrode here. In this case, I give an example using the tungsten oxide and vanadium lithiated vanadium pentoxide. It has initially a slightly yellowish color, as you see in here, and vanadium oxide has a dark blue color. So when the lithium ions move from electrolyte to the tungsten oxide, the material became color, dark blue color. If you change the polarity, then all lithium mobile ions will move back to the electrolyte or will move back to the tungsten oxide, then the device will be bleached. So this is the bleach state. Off state means bleach state, and on state means the color state. That's the reactions took over in the ion storage layer and electrochromic layer. Tungsten oxide in its original state is transparent, but when you reduce it became a deep blue. Lithiated tungsten oxide has a blue color. And ion storage layer of an electrochromic device, charge capacity of the counter electrode must be equal, at least equal or greater than the charge capacity of tungsten oxide films. This is a very important property. Counter electrode that I show you in the system was lithiated vanadium pentoxide. Determine the amount of the charge in the cell capable of reversible insertion of cations, not electrochromic, needs to be activated prior to or after the cell assembly. Electrochromic electrode, which is tungsten oxide, is transmission color in the color state is blue, and this is the reduction reaction that you can see. What are the advantages of using ion storage layer in the electrochromic device? First advantage is color memory. It has some memory that took took over some time. No self-bleaching, suitable for large area AC glass, means that suitable for Windows application. However, there are some disadvantages, like ion storage layer needs to be activated prior to or after the cell assembly. Ion storage layer is not electrochromic. Difficult to find an ion storage layer which are colorless in the reduced state. That's the device with having anodic and cathodic complementary electrochromic layers. The top is glass and coated with transparent conducting layers. Also, lower part is glass coated with counter electrochromic layer. We use very, very thin metallic layer, generally silver or platinum. Very thin is like 50 angstrom, the thickness is almost, there is nothing like that. And then we use the counter electrochromic layer. That should be the oxidized, that should be the anodic electrochromic material. And we have mobile ions in the ion conductor. This is the ion conducting material. And then we have a working electrolyte, which is the cathodic electrochromic layer. So that's the sandwich structure of the device that you've seen in this prototype. It's exactly the same structure. Coloration from both cathodic and anodic layers. The first reaction is electrochromic, occurs in the electrochromic cathodic electrolyte. Tungsten oxide in transparent case, when it has been reduced, this is reduced by proton insertion, they became blue. Electrochromic anodic electrode reaction is that in this sample I use the nickel hydroxide. Nickel hydroxide transparent, but when it oxidized, it became a brownish color. So if you use the blue and brownish color together, you obtain more natural color than the dark blue color. It became more natural. Devices with anodic and cathodic electrochromic layers. Application of DC potential. Tungsten trioxide is reduced and nickel hydroxide is oxidized. And what are the advantages of those devices? Memory, efficient use of charge in these devices. Since both anodic and cathodic layers are electrochromics, and color can be tuned to be natural by using these two complementary layers. Electrochromic devices with solution phase redox, and here is the typical structure: glass transparent conducting, glass transparent conducting. And this is cathodic electrochromic layer. It uses only one electrochromic layer. And you have an electrolyte with redox promoter in the sample. There are redox promoter, source of sink for electrons for oxidation and reduction of electrochromic layer. There are some redox promoters like ferrocene undergoes one electron oxidation at lower potential to another form, ferrocenium, as you've seen in here. So electrochromic devices with solution phase redox promote self-bleaching once color potential is removed. Used in electrochromic mirrors, Gentex uses this technique too. Zealand, Michigan. And scaling to large area is very difficult due to the higher power consumption to maintain the color state. So they are not used for the Windows application, for the architectural application. Now, commercially available electrochromic windows. Electrochromics windows for an aircraft. This one you see is taken from the Airbus 380 and electrochromic layers assembled by the Saint-Gobain company in France. And I was able to see and take the picture. I took this picture myself when I saw the system. Because the director of this research group was, still is, a friend of mine from Lawrence Berkeley National Lab. At that time, he was a PhD student at UC Berkeley. After he finished his PhD, he went back, he's a French guy, back to Saint-Gobain. And he became the director of this research project, and he got very successful actually. So this is basically, we can see them on the application for the airplanes. And interactive Windows systems, that's PPG, Pittsburgh Plate Glass Company, and also Gentex joint venture. Made also electrochromic device for the Boeing 787, in other words, Dreamliner. They also use this system. Large area convention windows, commercial windows. This picture is taken from the library of one of the community colleges in California. It is from the San Mateo Community College. Their library used this windows. So the windows are developed by Sage Corporation in Minnesota. EC glass size is 1.6 meters square. These are e-control glass, electronically controlled glass, electric field control glass. And the EC glass size is about 2.6 meters square. These are the two different corporations. Both use tungsten oxide as a layer. When you see the blue color, you are sure that this uses the tungsten oxide. And these are the examples. Now let's look at the transmittance properties of those windows on UV, visible, and near infrared range. This shows the typical transmittance in the bliss state, and this uses the color state. You see the color modulation, which is very high. Okay, now I want to talk about the requirement for an electrochromic window. It has been shown for solar transmitters and solar reflection values in the bleach and color state. BL stands for bleach state and COL stands for the color state. And the switching voltage property, memory, cycling time, operating temperature. As I told you before, this device should operate between minus 30 all the way to 70 centigrade degree. And they have to have a cycling time over 10 to the 4 or 16 cycles. And that corresponds to the lifetime 5 to 20 years. The one that I show you in San Mateo Community College Library, Sage gives a 10-year warranty for those glasses. But now the warranty increased to 15 years. Hopefully soon it will reach to 20 years period. This data is taken from my colleague. Actually, that's the reason I am here. Dr. Karl Lambert offered me a job when I was presenting my presentation, my work in Sicily, Erice. And he, after I make a presentation, he approached to me, he told me, oh, your technique is very interesting. I just received a grant from US Department of Energy. Do you mind to come and transfer your technique to us for a year? I can give you a salary and I can support you. And I say yes. So that's the story begins in 1983. Since then, he is one of my best friends. So because of him, I am living in United States. And Dr. Karl Lambert is the leader of the group for the International Energy Agency on the solar heating and cooling program. I am also a member of this group, and that reference, these results taken from his report that he submitted to the International Energy Agency. Now, properties of a large commercial electrochromic glasses. It operates at 5 volt DC. That's the maximum value, but you can, for the smaller size, you can use 1.2 or 3 volt. Lower power consumptions, which is lower, about 0.5 watt hour per meter square. Durability, more than 10 to 5 cycles. And 30 years lifetime between. These are the values that Sage Glass Company mentioned in their report. So it's 30 years when they cycle from, when they operate from 30 to 60 centigrade degree. Sage and E-Control Glass offer 10-year warranty on their electrochromic windows. And the manufacturer, I mentioned about the size of the devices and the transmittance value in solar spectra, visible, and cycles. The Sage one is 108 by 150 centimeters square. And the visible transmittance is between 60 to 35%. E-Control Glass, another company that makes the glasses, is larger size, 120 by 120. And this reference is taken from the Solar Energy Materials and Solar Cells Journal. And it has been published in 2010. If you are interested, it's a good article. I suggested you to read it. And the reference is here, volume number 94 and the page 87 to 105. And I am also editorial board member of Solar Energy Materials and Solar Cells. Now, commercial AC windows, what are the issues based on? All based on absorbing materials. Those devices are based on absorbing materials. Dye-based windows absorbs in visible and ultraviolet, but not in the near infrared. This is the typical solar radiation spectrum of those devices. Tungsten oxide-based windows modulate only a fraction of the spectrum. More than a half of the solar energy is below the reflection edge of tungsten oxide layer. So that limits the window efficiency and absorbed light in the re-radiated as a heat into the building. Commercial electrochromic windows, I mentioned the issues. Now, the last slide, conclusion. Electrochromic windows, many electrochromic device configuration involving reduction and oxidation reaction exist, but only 2 types have been commercialized. by the two companies, one of them Saint-Gobain and the other one is Sage Corporation. Devices based on electrochromic dyes in the electrolyte are used as a rear view or side view mirrors, and they have a lot of market, as up to 15 to 17 million EC mirrors per year. And windows in the aircraft also became a big contribution in the transportation field. Large area EC windows based on tungsten oxide as the electrochromic medium are commercially available. These are based on absorptive technology and require a spatial packaging, new electrochromic devices based on reflection are needed to allow the rejection of the entire thermal load. And there are a lot of study going on in this field. Instead of the electrochromic devices based on the absorption, now they are trying to find electrochromic device structure based on the reflection. There is a center at National Renewable Energy Laboratory doing active research on this field. Also, another group is at Lawrence Berkeley National Laboratory, Windows and Daylighting Group, also doing a research on this field. There are many companies, private companies, including Pilkington Glass in England, Shot Glass in Germany, and Sage in United States, and PPG in United States also doing a research on those fields. I cannot give some information about the research going on the private companies because it's confidential, but I have some friends works for those companies saying that they had good results, but I don't see any results yet. So this is end of my talk. I would like to thank you for your attention. Thank you.